Beneath the vast, rolling waves of today's oceans lies a secret, one that rewinds the clock millions of years to a time when the world looked nothing like it does now. Picture this: where saltwater now swirls, there once stood towering forests, their leaves rustling in a warm, tropical breeze. These weren't just any trees, they were giants, part of lush ecosystems that thrived in places now buried beneath the seafloor. And here's the astonishing part: their remains are still there, perfectly preserved in the darkness, waiting to tell their story. These ancient trees, hidden in the depths, are more than just relics of the past. They're time capsules, holding clues to a vanished world, one that could reshape how we understand our planet's future. What if I told you that the key to predicting tomorrow's climate might lie in these long-lost forests? Scientists are now pulling these submerged wonders from the ocean floor, uncovering not just wood, but entire ecosystems frozen in time. These discoveries reveal an Earth that was warmer, wetter, and teeming with life in places we'd never expect. Imagine walking through a rainforest where today you'd need a submarine. How did these landscapes vanish beneath the waves, and what forces of nature could possibly bury something as immense as a forest? The answers are as dramatic as they are revealing tales of shifting continents, rising seas, and climates that transformed beyond recognition. This isn't just about the past, though. Those ancient trees whisper warnings and wisdom for our own era of rapid environmental change. By studying them, we're piecing together how Earth's climate has flipped from one extreme to another, and what that means for us. So let's dive into this mystery together, exploring how scientists decode these underwater time capsules and what they tell us about the fragile balance of life on our planet. From the science that brings these forests back to life to the history hidden in their rings, this is a journey to the heart of one of nature's most astonishing secrets. Ready to uncover the lost world beneath the waves? Let's begin. The story of how these ancient trees were discovered reads like something out of a scientific detective novel. It all began with marine geologists scanning the ocean floor, not for lost forests, but for clues about underwater terrain. As their sonar equipment sent pulses of sound through the dark water, something unexpected appeared on their screens: odd, linear shapes where there should have been only smooth sediment. At first, they assumed these were geological formations, perhaps ridges of rock carved by ancient currents. But when underwater cameras finally revealed the truth, the scientific community was stunned. Those weren't rocks at all, they were the skeletal remains of massive tree trunks, some still standing upright as if frozen in time. What makes these findings so extraordinary isn't just their age, though some of these trees date back more than 10,000 years. It's how perfectly they've been preserved. Buried in layers of silt where oxygen couldn't reach them, these ancient giants avoided the decay that would have turned them to dust on land. Instead, they became time capsules, their rings holding precise records of the climates they once thrived in. Scientists used carbon dating to pinpoint their age, but the real revelations came from studying the sediment around them. The layers of mud and sand told a parallel story, one of sudden submergence, where rising seas swallowed entire landscapes in what might have been just a few generations. This discovery didn't just add a new chapter to Earth's history, it rewrote old assumptions. Before these trees were found, many researchers believed sea level rise happened at a slow, steady pace. But the evidence told a different tale. Some of these forests were buried so quickly that their leaves and even insects were preserved alongside them, suggesting catastrophic flooding or rapid environmental shifts. Suddenly, the narrative of a gradually changing planet had to make room for moments of dramatic transformation. And that's what makes these underwater forests more than just relics. They're proof that Earth's climate has flipped between extremes before, and they force us to ask, could it happen again? To stand in one of these ancient forests would have been like stepping into a living greenhouse, a world so lush and vibrant. It makes today's tropical rainforest seem almost tame by comparison. The air would have hung thick with moisture, carrying the earthy scent of decaying vegetation and the sweet perfume of early flowering plants, some of which had only recently evolved. Towering trees, their trunks wider than cars, formed a dense canopy that filtered sunlight into a dappled green haze. Beneath them, a tangled understory of giant ferns and creeping vines thrived in the perpetual humidity, while dragonflies the size of songbirds darted between towering horsetail reeds. The clues to this lost world don't just come from the trees themselves. Scientists have sifted through layers of sediment like detectives, piecing together a crime scene, uncovering pollen grains so perfectly preserved they reveal the exact species of plants that once grew here. These microscopic time capsules tell us this wasn't just any forest, it was a biodiversity hotspot, home to plants and animals that have no modern equivalents. Imagine walking through a landscape where primitive relatives of magnolias and figs grew alongside strange, now extinct shrubs, their leaves adapted to a climate that never knew frost. But perhaps the most striking feature of this vanished ecosystem was its water. Rivers wider than the Amazon meandered across the land, their banks lined with sprawling wetlands that acted like natural sponges, stabilizing the environment and nurturing an explosion of life. Fossilized insect wings and fish scales found in the same sediment layers suggest these waterways teemed with creatures, from freshwater mollusks to early amphibians. It was a world in constant motion, shaped by the push and pull of water and growth, a far cry from the silent ocean floor that now blankets it. What's truly humbling is realizing how recently, in geological terms, this transformation occurred. In some places, the shift from thriving forest to submerged graveyard may have taken only a few centuries, a blink of an eye in Earth's timeline. That rapid change mirrors the climate upheavals we're witnessing today, making these ancient forests more than just a curiosity. They're a mirror reflecting back at us the delicate balance that sustains life and the staggering speed at which it can all be rewritten. Unlocking the secrets of these submerged forests requires more than just diving equipment. It demands cutting-edge technology that would have seemed like science fiction just decades ago. Modern researchers deploy a dazzling array of tools, each designed to peel back layers of time with surgical precision. Autonomous underwater drones glide through the darkness, their high-resolution cameras and sonar systems creating detailed three-dimensional maps of the seafloor. These digital reconstructions reveal not just individual trees, but entire preserved landscapes, showing how rivers once curved between ancient hills now buried under sediment. But the real magic happens when scientists extract core samples, long, cylindrical plugs of seabed sediment that act like vertical timelines. Each layer of mud and sand holds trapped pollen grains, leaf fragments, and even microscopic organisms, all perfectly preserved in their watery tomb. In laboratories, researchers analyze these samples with techniques so sensitive they can detect the chemical signatures of individual raindrops that fell thousands of years ago. Oxygen isotopes in tree rings become ancient thermometers, telling us whether a particular century was warmer or cooler. Carbon isotopes reveal how much carbon dioxide filled the air when these trees were alive, painting a startlingly precise picture of prehistoric atmospheres. Perhaps most astonishing is how genetic material survives in these submerged time capsules. specialized equipment can now extract and sequence degraded DNA from waterlogged wood and plant matter, allowing scientists to reconstruct the genetic blueprints of long-vanished species. These genetic ghosts show how plants adapted to changing climates, information that could prove invaluable as we face our own environmental shifts. Meanwhile, laser ablation technology vaporizes tiny sections of wood to analyze their elemental composition, revealing patterns of drought and rainfall with resolution so fine it can distinguish between individual growing seasons. What emerges from all this data isn't just a snapshot, it's a high-definition movie of Earth's past. By combining these techniques, researchers can track how temperatures fluctuated, how storm patterns shifted, and how ecosystems transformed over millennia. The submerged forests become more than archaeological curiosities. They're living libraries, their pages written in cellulose and sediment, waiting to teach us how our planet breathes, changes, and occasionally reinvents itself entirely. And as our tools grow ever more sophisticated, who knows what other forgotten worlds we'll uncover beneath the waves? These ancient underwater trees hold secrets in their rings. Each groove and line a precise record of the world as it was thousands of years ago. Think of them as nature's own weather stations, meticulously logging every shift in temperature, every stretch of drought, every season of plenty. When conditions were ideal warm temperatures, steady rainfall, the trees grew rapidly, leaving behind wide, bold rings. But during hard times, years when rain was scarce or temperatures dropped, the rings tightened like a clenched fist, preserving the memory of struggle in their narrow bands. What makes these submerged specimens so valuable isn't just their age, but their uninterrupted timelines. Unlike trees on land, which might be lost to fire or decay, these were sealed away in oxygen-starved seabeds, their records perfectly intact. Scientists can trace not just decades, but entire centuries of climate history in a single trunk. By cross-referencing these patterns with ice cores, cave formations, and soil layers from the same period, they've pieced together a startlingly detailed picture of Earth's ancient weather. One of the most striking revelations, these trees lived through climate swings far more dramatic than anything we've experienced in modern times. Some rings tell of decades-long megadroughts that would reshape entire regions today. Others hint at sudden, violent shifts, at periods when the climate seemed to flip like a switch, turning wet landscapes arid in just a few generations. And here's what's truly sobering: many of these changes occurred without human influence. They were the result of natural cycles, volcanic eruptions, or subtle shifts in Earth's orbit. Yet they still brought upheaval, proof that our planet's climate has always been restless, capable of rapid transformation even without industrial interference. This raises an urgent question for our own era. If ancient trees witnessed such volatility long before factories or cars existed, what might happen now with greenhouse gases accelerating the process? The answer lies in the patterns. By studying how ecosystems coped or collapsed in the past, researchers can model potential futures. Some of these submerged forests, for example, thrived in carbon dioxide levels similar to what we're approaching today. Their rings reveal bursts of growth initially as plants gorged on the extra CO2, but over time the benefits faded as temperatures soared and rainfall patterns fractured. It's a warning written in wood. Even short-term gains can unravel when larger systems shift. Perhaps the most humbling lesson from these silent witnesses is how interconnected everything really is. A drought recorded in a tree ring off today's coast might match ash layers from a volcano on the other side of the world, or sediment from a vanished lake halfway between them. The trees didn't just grow in isolation, they responded to global forces just as our modern climate does, and that's why these drowned forests matter more than ever. They remind us that climate change isn't an abstract future threat. It's a recurring chapter in Earth's story, one we're now helping to write faster than ever before. The real mystery isn't whether the climate can change. We know it can, and drastically. It's whether we'll heed the warnings buried beneath the waves. The story of how oceans swallowed these ancient forests is written in the rising tides of history, a drama that unfolded as the last ice age breathed its final melting sighs. Picture vast sheets of glacial ice, some towering taller than skyscrapers, retreating across continents as temperatures climbed. All that frozen water had to go somewhere, and as it poured into the seas, coastlines were redrawn at a pace that would stagger modern observers. We're not talking about gradual inches per century. These were surges that could drown entire forests in just a few human lifetimes. Scientists have pieced together this aquatic invasion from the very trees it claimed. The submerged trunks hold telltale signs of saltwater intrusion in their outermost rings, abrupt shifts in cellular structure where freshwater roots suddenly found themselves bathed in brine. Sediment layers tell an even starker story. In some places, mats of preserved leaves lie buried beneath 10 feet of marine mud, as if the land simply sank overnight. These weren't gentle floods, they were environmental revolutions, transforming thriving ecosystems into underwater graveyards with terrifying efficiency. What's truly sobering is how familiar this ancient catastrophe feels today. Current satellite data shows modern sea levels rising nearly 3 times faster than they did for most of the 20th century, a trend that mirrors the accelerations recorded in those drowned forests. Back then, the drivers were natural: the wobble of Earth's orbit, the rebound of tectonic plates freed from glacial weight. Now, human activity is the force reshaping coastlines. But the outcome could be eerily similar: wetlands and woodlands surrendering to the waves, their stories preserved in mud for future scientists to uncover. The parallels don't end there. Just as the Ice Age floods caught ecosystems mid-transformation, today's coastal forests face the same brutal mismatch between adaptation and speed. Mangroves can migrate inland, but only if development doesn't block their path. Saltwater-tolerant plants can evolve, but not in decades. These ancient submerged forests stand as silent witnesses to a truth we're just beginning to grasp. When seas rise fast enough, even the most resilient landscapes can't outrun them. Yet within this warning lies a strange hope. Those preserved trees prove that nature has weathered such shocks before, not unscathed, but with a stubborn persistence that reshuffles rather than erases life. The lesson isn't just about loss, it's about transformation. As we study these time capsules, we're not just reading a eulogy for drowned forests. We're deciphering a survival manual, one written in rings and sediment waiting beneath the waves. Buried alongside those ancient tree trunks, scientists have uncovered an entire menagerie of lost life, tiny time travelers preserved in exquisite detail. Imagine brushing away layers of seabed sediment to reveal the delicate wing of a beetle that last fluttered through prehistoric air, or the perfectly round imprint of a bird's foot pressed into mud that hasn't seen sunlight in millennia. These aren't just random fragments, they're pieces of a puzzle, each one helping reconstruct an ecosystem that vanished when the seas rolled in. Take the insects, for instance. Some of the best preserved specimens look almost modern at first glance until you notice the subtle differences. A wasp's wing might be broader, its veins arranged in a pattern no living species shares. A spider's leg might end in a claw shape unseen in today's rainforests. These creatures weren't just passing through, they were specialists, finely tuned to a world that no longer exists. Their very strangeness hints at evolutionary experiments that flourished for thousands of years, only to disappear when their habitat drowned. Then there are the seeds, hundreds of them, some no bigger than a grain of sand, others as large as walnuts. Mixed into the sediment like botanical confetti, they represent the forest's next generation, the trees that never grew. Modern scanners can peer inside these fossilized casings, revealing embryos frozen in mid-development. Some match known plant families, distant relatives of today's mangroves or palms. Others defy classification, their structures so unique they represent entire lineages snuffed out by rising waters. But perhaps the most haunting finds are the tracks, not fossils exactly, but fleeting moments preserved in mud. A crocodilian's belly drag along a riverbank. The skittering steps of a small mammal fleeing some long-forgotten threat. These ghostly impressions capture motion, behavior, the daily rhythms of a living world. Unlike bones or shells, tracks require perfect conditions to fossilize. Just enough moisture to make an impression, then rapid burial to seal it before erosion can steal it away. That so many survived suggests these forests didn't fade gently. They were buried alive, their stories cut short mid-sentence. What emerges from all these fragments is a paradox. On one hand, this was a thriving, interconnected web of life, buzzing with species we're only beginning to understand. On the other, it was fragile, a house of cards that collapsed when the climate shifted. Some organisms, like certain ferns and mollusks, have living descendants that adapted to new conditions. Others left no heirs, their genetic blueprints erased forever. And that's the real lesson lurking in this underwater museum. Extinction isn't always dramatic. Sometimes it's quiet, the slow drowning of possibilities, one species at a time, until an entire way of life slips beneath the waves. Now, as we face our own era of rapid environmental change, these lost ecosystems offer a sobering preview. The same forces that reshaped their world, rising temperatures, shifting coastlines, are at work today. Will our modern species adapt like the survivors in the sediment, or vanish like those wasps with the unfamiliar wings? The answer might lie in the mud waiting to be read. Long before scientists began piling together this ancient climate puzzle, there were people who walked among these towering forests, people who watched as the waters crept steadily inland. Along coastlines from the North Sea to the Gulf of Mexico, archaeologists have uncovered stone tools and fishing weirs submerged in areas that were once dry land, proof that human communities lived, hunted, and thrived in these now drowned landscapes. Some of these artifacts date back more than 8,000 years, placing them squarely in the era when rising seas were swallowing entire forests. What must it have been like to witness such change, to see familiar hunting grounds vanish beneath the waves, or to watch ancient trees slowly succumb to salt water? Remarkably, we may already have fragments of those memories preserved, not in sediment but in stories. Indigenous oral traditions from coastal regions around the world speak of great floods, of lands lost beneath the sea, of ancestors forced to flee rising waters. The Aboriginal peoples of Australia, for instance, recount tales of shorelines that once stretched far beyond today's coasts, while Native American tribes along the Pacific Northwest describe villages submerged by a relentless ocean. These aren't just myths, they're cultural time capsules, echoing events that align startlingly well with the geological record. When a story persists across hundreds of generations, it often carries a kernel of truth, a shared memory of catastrophe reshaped by time into legend. The physical evidence left behind by these early communities tells its own story. In the Baltic Sea, divers have found fishing traps made of woven branches, technology unchanged for millennia, lying amid the stumps of drowned oak forests. In the Americas, shell middens mark former coastal settlements now stranded underwater, their discarded meals of clams and oysters silent witnesses to abandoned homes. These finds reveal a pattern of adaptation and retreat as communities shifted inland, following the receding shoreline or adapting to new ways of life. Some turned to boats, becoming seafarers where they had once been forest dwellers. Others developed new tools to harvest marine resources, trading axes for nets in a world reshaped by water. What's perhaps most striking is how these ancient upheavals mirror challenges we face today. When the forests drowned, they didn't vanish overnight. The process spanned generations, long enough for people to adjust, but also long enough for the cumulative loss to reshape cultures. Sound familiar? Modern island nations grappling with rising seas are living through a similar slow-motion crisis, one that demands not just survival but reinvention. The difference, of course, is scale. Where ancient communities had empty lands to migrate into, today's displaced populations confront borders and cities. Yet the core lesson remains: humanity has weathered such transformations before, not without cost, but with stubborn creativity. Perhaps that's the real gift these submerged forests offer, not just warnings, but proof of resilience. The tools left behind, the stories passed down, even the genetic traces of coastal peoples in modern populations, all whisper the same truth: change, even catastrophic change, is survivable. Not unchanged, not unscathed, but with new ways to live forged in the crucible of necessity. As we study these ancient echoes, we're not just uncovering lost history. We're rediscovering an old, hard-won wisdom, one we may need sooner than we think. The ground beneath these ancient forests was never truly still. It shifted, groaned, and occasionally gave way with catastrophic consequences. While rising seas played the starring role in drowning these landscapes, tectonic forces lurked in the background like unseen stagehands, reshaping coastlines with slow but relentless power. Picture a massive puzzle where the pieces, Earth's tectonic plates, are constantly jostling for position. Where these plates collided or stretched apart, entire regions could rise or sink like elevators, accelerating the ocean's advance in some places while holding it at bay in others. Take the submerged cypress forests off the coast of Alabama, preserved in what was once a river valley. Core samples reveal layers of sand suddenly interrupted by thick mats of organic material, a telltale sign that the land didn't just flood, but dropped several feet in a geological instant. Seismic surveys trace this collapse to a fault line still active today, where occasional tremors remind us that the Earth's crust remains restless. Similar stories unfold worldwide. In New Zealand, entire stands of ancient kauri trees now lie 60 feet underwater, their roots still clinging to soil that plunged downward during a massive earthquake over 5,000 years ago. Volcanoes added another layer of chaos to this already dramatic process. Ash layers sandwiched between sediment near these submerged forests tell of eruptions that darkened skies for years, triggering climate shifts that stressed ecosystems already battling rising waters. Some coastal forests may have met their end not from gradual flooding, but from tsunamis, colossal waves generated by undersea earthquakes that scoured entire landscapes in minutes. Imagine a wall of water carrying not just salt, but steaming debris from volcanic explosions, battering trees that had stood for centuries. Yet paradoxically, these same violent forces also acted as preservatives. When land sank rapidly along fault lines, forests were often buried under thick layers of silt before decay could set in. Oxygen-starved environments created by tectonic subsidence became natural time capsules, sealing wood, leaves, and even insects in a state of suspended animation. In contrast, areas where the crust slowly uplifted exposed forests to erosion, leaving little behind but scattered fragments. This uneven hand of geology explains why some coastal regions boast perfectly preserved underwater forests, while others show only traces of their prehistoric greenery. What's truly humbling is realizing how small these events were in geological terms, mere hiccups in the planet's long history. A fault slip here, a volcanic burp there, and entire ecosystems vanished from the land's memory. Yet their legacy endures, offering us more than just climate clues. These submerged forests are reminders that the ground we think of as solid is anything but, a truth that resonates uncomfortably today. As modern sea levels rise, cities from Jakarta to New Orleans aren't just battling water, they're sinking on land that's still adjusting to ancient tectonic shifts. The past isn't just buried beneath the waves, it's still shaping the ground beneath our feet. To understand those ancient submerged forests, we need only look to the tangled, salt-tolerant mangroves lining today's tropical coasts. These modern ecosystems are the closest living relatives to the lost worlds beneath the waves, places where trees stand half-submerged in brackish water, their looping roots forming labyrinths that shelter crabs, fish, and nesting birds. Like their prehistoric counterparts, mangroves thrive in the delicate balance between land and sea, building new soil from fallen leaves and trapping sediment with their intricate root systems. But here's the haunting parallel. Just as rising seas once drowned those ancient forests, mangroves worldwide are now retreating inland or dying off where coastal development blocks their escape. Peat swamps tell another chapter of this story. These waterlogged forests, found from Indonesia to the Amazon, are time machines of sorts. Their acidic, oxygen-poor waters slow decay to a crawl, allowing layers of organic matter to accumulate over centuries. Scientists drilling into these swamps uncover preserved plant matter so fresh-looking it could have fallen last season, not thousands of years ago. This remarkable preservation mirrors the conditions that saved our submerged forests, offering a living laboratory to study how organic material resists decay. Yet these swamps face dual threats. Drained for agriculture, their dried peat releases ancient carbon into the atmosphere, while rising seas salinate soils that freshwater plants can't tolerate. What makes these modern ecosystems so valuable isn't just their resemblance to the past, it's how they help scientists test theories about prehistoric environmental shifts. By monitoring how mangroves respond to today's rising sea levels, researchers can refine models of how their ancient relatives succumbed. When a modern peat swamp floods, the changes in its plant chemistry leave behind a signature that can be matched against sediment layers from drowned forests. These living experiments provide something fossils alone cannot: real-time data on the pace and pattern of ecosystem collapse. The urgency to protect these areas has never been clearer. Mangroves and peat swamps aren't just ecological curiosities, they're biodiversity hotspots and carbon storage powerhouses. A single acre of mangrove forest can sequester 4 times more carbon than a similar patch of rainforest, while peatlands hold nearly twice as much carbon as all the world's forests combined. Losing them wouldn't just erase living links to prehistoric worlds, it would accelerate the very climate changes that doomed their ancient counterparts. Perhaps the most profound lesson lies in the resilience hidden within these ecosystems. In Florida's 10,000 islands, mangroves have been observed migrating inland at rates of nearly 100 feet per year, a slow-motion sprint to outpace rising waters. Some peat swamps, meanwhile, are adapting by growing vertically, building their own elevation through accumulating debris. These strategies echo the ways ancient forests might have resisted or succumbed to environmental shifts. The difference now is that humans aren't just observers, we're both the threat and the potential solution. By protecting these living analogs, we're not just conserving nature, we're preserving a manual for survival, written in roots and mud for whatever changes lie ahead. The hunt for these ancient underwater forests has entered a new era, powered by technologies that would have seemed like pure science fiction to researchers just a few decades ago. At the forefront is LiDAR, a laser-based scanning system originally developed for mapping battlefields that's now revealing lost landscapes beneath the waves. Mounted on boats or aircraft, these instruments fire millions of light pulses per second, penetrating shallow water to create high-resolution maps of submerged terrain. What makes LiDAR revolutionary isn't just its precision, but its ability to cover vast areas quickly, where divers might spend years painstakingly documenting a single forest. LiDAR can survey entire coastlines in days, uncovering hidden tree stumps, river channels, and even human-made structures invisible to conventional sonar. But raw data is just the beginning. Modern artificial intelligence acts like a tireless research assistant, sifting through mountains of LiDAR scans and sonar readings to spot patterns no human eye could catch. Machine learning algorithms trained on known submerged forests can identify similar formations in uncharted waters, flagging potential sites for closer inspection. These AI systems don't replace scientists, they supercharge them, filtering out false positives and highlighting the most promising anomalies. In the Gulf of Mexico, this tech has already pinpointed previously overlooked cypress stands buried under 30 feet of sediment, their locations betrayed by subtle variations in seafloor composition that algorithms detected long before divers confirmed them. The real game changer lies in how these tools work together. Autonomous underwater drones equipped with LiDAR and high-definition cameras can navigate treacherous currents or murky waters too dangerous for human explorers. When they discover something intriguing, robotic arms collect core samples with surgical precision, while onboard sensors analyze chemical traces in real time. Back onshore, virtual reality systems allow researchers to walk through digital reconstructions of these lost landscapes, studying tree distributions and terrain features from every angle. It's paleoecology meets space-age tech, a fusion that's rewriting what we thought possible. Perhaps most exciting are the indirect discoveries these methods enable. By mapping submerged river systems that once fed these forests, scientists have located entirely new categories of archaeological sites, hunting camps, tool-making stations, even ceremonial grounds that were dry land when the trees thrived. Advanced spectral imaging can detect minute changes in sediment chemistry, revealing where freshwater springs once bubbled up, creating oases that attracted both wildlife and ancient humans. Each technological leap peels back another layer of time, turning what were once vague hypotheses into detailed, testable models of prehistoric ecosystems. What's emerging isn't just a catalogue of lost forests, but a dynamic understanding of how they lived and died. LiDAR-derived elevation models show exactly how rising waters advanced across the landscape, while AI analysis of tree rings correlates local events with global climate shifts. We're no longer limited to studying these ecosystems in isolated snapshots. We can watch them evolve across centuries, witnessing the slow drama of environmental change play out in 3 dimensions. And as these tools grow ever more sophisticated, who knows what other forgotten worlds await discovery beneath the waves? The ocean's secrets are vast, but our capacity to uncover them is growing faster than ever. Beneath the turquoise waters of the Gulf of Mexico, 60 feet down, lies a haunting relic from Earth's past, an entire forest frozen in time. These aren't petrified trees turned to stone, but actual cypress trunks, their bark still intact, their wood so fresh it releases the earthy scent of sap when scratched. This is Alabama's underwater forest, a sprawling time capsule from the Pleistocene epoch, hidden for 60,000 years until Hurricane Ivan's fury ripped away its sandy shroud in 2004. What makes this discovery extraordinary isn't just the forest's age, but its surreal preservation. Unlike typical fossils, these trees never mineralized. They were buried so quickly under layers of sediment that decay couldn't keep up. Dive down today and you'll find towering trunks still rooted in their original soil, their branches long gone but their bases forming ghostly avenues across the seafloor. Marine biologists initially thought they'd stumbled upon a shipwreck's debris field until they brushed away the sand and realized these were the remains of a vibrant wetland, one that thrived when mammoths still roamed the continent. The scientific gold mine here lies in the details. Core samples extracted from the tree's rings reveal a climate far cooler than modern Alabama, with sharp spikes of drought that stress the forest periodically. Pollen grains trapped in the surrounding mud tell of a diverse ecosystem: grasses, shrubs, and water plants that supported everything from insects to giant ground sloths. But the real revelation came when researchers carbon dated the wood. The forest didn't drown gradually as seas rose after the last ice age. It was swallowed catastrophically, likely by a rapid subsidence of the land or a monstrous storm surge. One layer of sediment shows a clean break between freshwater peat and marine sand, suggesting the ocean claimed this land in a geological instant. For archaeologists, the site holds even deeper intrigue. Scattered among the roots are stone tools and charred wood fragments, evidence that humans once foraged here. Imagine standing in that ancient swamp, listening to the calls of now extinct birds, unaware that the very ground beneath you would one day vanish beneath the waves. That tangible connection to our ancestors is what makes this submerged forest more than a curiosity. It's a bridge across millennia, reminding us how fleeting our own landscapes might be. Now, as scientists race to document the site before saltwater erodes its fragile wood, the forest faces a new threat: curiosity. Looters have already hacked off chunks of timber, drawn by the novelty of 60,000-year-old lumber. Conservationists are working to balance access with preservation, knowing this rare window into the past could slam shut any day. Yet even as individual trees crumble, their legacy endures in the data they've provided: proof that Earth's most profound stories aren't always written in stone. Sometimes they're waiting beneath the waves, whispering secrets in the language of bark and mud. While Alabama's underwater forest offers a stunning glimpse into the past, it's far from alone. Scattered across the globe, these submerged time capsules form a network of natural archives, each preserving unique chapters of Earth's environmental history. Take the North Sea, for example. Beneath its churning grey waves lies Doggerland, a vast prehistoric landscape that once connected Britain to mainland Europe. Fishermen trawling these waters have hauled up more than just fish for centuries. Their nets occasionally bring aboard antlers, stone tools, and chunks of peat from forests that flourished over 8,000 years ago. Unlike Alabama's sudden burial, Doggerland's forests met a slower fate, gradually inundated as melting glaciers filled ocean basins. The difference in their endings is etched into the wood itself. Where Alabama's cypress rings show abrupt stress signals, Doggerland's oaks record a lingering struggle against encroaching saltwater. Venture to the Baltic Sea and the story shifts again. Here, cold, brackish waters with low oxygen levels have preserved entire stands of pine trees so impeccably that their resin still smells fresh when disturbed. These forests didn't drown from rising seas alone. They were also victims of post-glacial rebound, a phenomenon where land masses, freed from the crushing weight of ice sheets, literally sprang upward in some regions while neighboring areas sank. The result, a patchwork of submerged and elevated forests that helps scientists map ancient sea levels with remarkable precision. In one extraordinary case off Sweden's coast, divers discovered a pine tree rooted in what was once a lakeshore, its top sheared off by a glacier's advance, its base later submerged as the land adjusted. Two climate catastrophes captured in a single specimen. Wales tells a different tale entirely. Along its western coast, the stumps of an ancient oak forest emerge at low tide, their roots tangled in sediments that whisper of a sudden, violent end. Geological evidence points to a mega tsunami triggered by an underwater landslide near Norway around 6,000 years ago, a wall of water that raced across the Atlantic, swallowing coastal woodlands in minutes. The tree's twisted trunks and jumbled branches paint a vivid picture of catastrophe, preserved like a prehistoric Pompeii beneath the waves. Meanwhile, on the other side of the world, New Zealand's submerged kauri forests add another layer to the narrative. These giants fell not to rising seas, but to a dramatic drop in sea level during a brief cold snap, which left them exposed on dry land long enough to die and fossilize before the ocean reclaimed them. What emerges from these global discoveries isn't just a collection of local curiosities, it's a mosaic of planetary change. By comparing the Baltic's glacially influenced forests with Alabama's tectonically drowned cypress stands, or contrasting Wales' tsunami-buried oaks with New Zealand's sea-level-rattled kauri, scientists can separate regional events from worldwide patterns. The real power lies in the contrasts. Why did some forests vanish abruptly while others faded over centuries? How did latitude affect their resilience? The answers are rewriting textbooks, revealing that climate change never plays out uniformly. It's a symphony of interconnected processes, with each region responding in its own way. And the search is far from over. From Japan's submerged cedar forests to potential sites off South Africa's coast, new discoveries continue to expand this underwater atlas. Every fresh find adds another piece to the puzzle, helping predict how today's coastlines might fare in a warming world. Because if there's one lesson these ancient forests shout from the depths, it's that history doesn't just repeat itself, it rhymes, with each era adding its own verse to Earth's enduring song of change. The secret behind these ancient trees' miraculous preservation lies in the very environment that swallowed them, a combination of chemistry, geology, and sheer luck that transformed them into natural time capsules. Water, normally an agent of decay, became their protector when certain conditions aligned perfectly. In the absence of oxygen, the microorganisms responsible for breaking down organic materials simply can't survive. Submerged in these watery tombs, the trees avoided the fungi and bacteria that would have turned them to dust on land, instead entering a state of suspended animation that lasted millennia. But oxygen deprivation was only part of the equation. Many of these forests were buried under sudden avalanches of fine silt sediment so dense it acted like nature's vacuum seal. When rivers flooded or storms churned up the seafloor, clouds of particles settled over the trees, filling every crevice and creating an impenetrable barrier against decay. Picture pouring concrete over a freshly picked bouquet. The flowers might wither slowly inside, but their shape would remain frozen in the hardened material. That's essentially what happened to these ancient giants, with silt replacing concrete and centuries replacing days. The water itself sometimes lent a helping hand. In places like the Baltic Sea, unusually low salinity and high acidity created a pickling effect, similar to how vinegar preserves cucumbers. Tannins leaching from the wood further discouraged bacterial growth, turning entire stands of trees into something resembling giant tea bags steeping in a cold, dark brew. Meanwhile, in rare coastal areas with high mineral content, a more dramatic transformation occurred: petrification, where silica or calcium carbonate gradually replaced the wood's cellular structure molecule by molecule, leaving behind stone replicas so detailed they still show growth rings under a microscope. What's truly astonishing is how these preservation methods captured more than just tree trunks. In the oxygen-starved mud surrounding the wood, scientists have found intact pine cones with their scales still closed, leaves with their veins perfectly visible, and even insect wings so delicate they disintegrate at a touch if exposed to air. These aren't just fossils, they're snapshots, freezing moments in time with a clarity that even the finest amber inclusions can't match. A beetle's last meal preserved in its gut, a fungus mid-growth on a leaf, the precise angle at which a branch fell, all locked away in the deep's natural vault. This level of preservation does more than satisfy scientific curiosity. By comparing these pristine specimens to modern plants, researchers can track evolutionary changes down to the cellular level, watching how species adapted or failed to adapt to shifting climates. The tree's cell walls reveal patterns of drought and rainfall. Their chemical makeup records atmospheric changes, and their very presence maps forgotten landscapes. Each well-preserved forest is like finding a library where the books haven't faded, a rare chance to read Earth's history exactly as it was written, without the usual gaps and guesswork. Yet for all we've learned, these underwater forests still guard mysteries. Why did some trees petrify while others merely mummified? How did certain insects survive long enough to be entombed with their host trees? Every answer uncovers new questions, reminding us that nature's archives are far more intricate than we imagined. The oceans didn't just hide these forests, they saved them, gifting us with windows into worlds we thought were lost forever. And as exploration technology improves, who knows what other preserved wonders might be waiting in the deep, ready to rewrite our understanding of the past. Those ancient forests now lying beneath the waves were once as vibrant and seemingly permanent as the Amazon or Congo basin are today, until forces beyond their control rewrote their fate. This stark parallel between past and present presses an urgent question onto modern conservation efforts. How do we protect today's critical ecosystems from suffering the same submerged fate? The answers aren't just hidden in sediment layers, they're unfolding in real time along vanishing coastlines and in shrinking habitats worldwide. Take mangrove forests, Earth's living armor against rising seas. Like their prehistoric predecessors, these salt-tolerant trees form dense barriers that stabilize coastlines, shelter marine life, and lock away carbon at astonishing rates. Yet nearly half of the world's mangroves have disappeared in the last century, cleared for shrimp farms or waterfront development. Their decline mirrors the early stages of those ancient drownings piece by piece. A resilient ecosystem is dismantled until one day, the cumulative loss becomes irreversible. The difference this time, we're not just passive witnesses to the change, we're the driving force behind it. Peat swamps tell a similar cautionary tale. These waterlogged forests store more carbon than all other vegetation combined, just as their ancient counterparts did before submersion. When drained for palm oil plantations or agriculture, they don't just stop absorbing carbon. They release millennia of stored greenhouse gases in a geologically instant belch of decomposition. Indonesia's peatlands alone emit more carbon annually than the entire nation of Germany, a modern echo of how decomposing drowned forests may have once altered prehistoric atmospheres. The lesson is unmistakable: disrupt these systems, and they transform from climate allies to climate time bombs. Yet within these warnings lies a roadmap for hope. Studies of how certain prehistoric species survived environmental upheaval are guiding modern, assisted migration projects, human-facilitated relocations of trees to more hospitable climates as their native ranges warm. In the Pacific Northwest, foresters are planting coastal redwoods farther north than they've grown in recorded history, mimicking patterns seen in ancient pollen records. Other initiatives draw direct inspiration from the past, restoring oyster reefs and seagrass beds to replicate the natural buffers that once protected those vanished forests from storm surges. Nature itself offers blueprints for resilience if we're willing to read them. The most profound insight from these underwater time capsules isn't just about fragility, it's about interconnectedness. Sediment cores reveal how the collapse of one species triggered cascading failures across entire ecosystems. A vanished pollinator here, a key tree species there, and slowly, the whole web unraveled. Modern conservation is applying this hindsight by focusing on keystone species, whose protection bolsters entire communities. The return of wolves to Yellowstone, for instance, didn't just control deer populations, it reshaped rivers by altering grazing patterns. This systemic approach mirrors what we now understand about those ancient forests. Saving individual species matters, but preserving the relationships between them is what truly maintains equilibrium. What separates our era from those past extinctions is agency. Where prehistoric forests faced inexorable natural forces, we're now the architects of change, for better or worse. Coral reefs bleached by warming oceans can regrow if given respite. Deforested lands can rebound when protected. Even the pace of glacial melt isn't entirely predetermined. The submerged forests stand as silent witnesses to what happens when systems tip past recovery. But they also whisper this reminder: collapse isn't inevitable until the last tree falls. Their legacy isn't just a warning, it's a challenge, written in rings and sediment, waiting for us to rise to it. The discoveries emerging from these submerged forests are doing more than rewriting history, they're revolutionizing how we teach it. Classrooms from elementary schools to PhD programs are buzzing with fresh insights, as paleoclimatology textbooks undergo updates to include findings that were pure speculation just a decade ago. Gone are the simplistic models of gradual climate change. In their place, students now examine sediment cores and tree ring data that reveal Earth's capacity for sudden, dramatic shifts. At the University of Southampton, marine archaeology students don wetsuits alongside their notebooks, training to document underwater sites with the same rigor as land-based digs. These aren't just academic exercises, they're preparing the next generation of scientists to interpret climate signals hidden in unlikely places. Museums worldwide are racing to bring these wonders to the public, transforming abstract scientific concepts into visceral experiences. The Smithsonian's Ocean Hall now features a cross-section of a 10,000-year-old cypress trunk, its rings annotated with major historical events: the eruption of Mount Vesuvius, the dawn of agriculture visible as faint lines in the wood. Interactive displays let visitors virtually dive through reconstructed forests, watching ecosystems transform as sea levels rise. Across the Atlantic, Stockholm's Vasa Museum has partnered with marine geologists to showcase Baltic pine specimens so perfectly preserved they still ooze resin under glass. These exhibits do more than educate. They spark wonder, connecting museum goers to prehistoric worlds through the tangible evidence of their demise. What's truly groundbreaking is how these discoveries have democratized science. Citizen scientists armed with snorkels and smartphones now contribute to global databases through initiatives like Submerged Forests Watch. Enthusiasts from Florida to Norway photograph exposed tree roots during extreme low tides, uploading GPS-tagged images that help researchers track erosion or identify new sites. In Wales, retired fishermen teach university teams to interpret sonar readings, their decades of local knowledge proving invaluable in locating ancient river channels now hidden beneath the waves. This collaborative approach has turned thousands of ordinary people into active participants in climate research, blurring the line between professional and amateur in the best possible way. The ripple effects extend beyond traditional science disciplines. Artists draw inspiration from scans of drowned landscapes, creating haunting installations that visualize lost worlds. Urban planners study prehistoric coastal adaptation strategies to design flood-resistant cities. Even ethicists weigh in, using these forests as case studies for environmental stewardship in the face of inevitable change. The educational impact isn't confined to lecture halls. It's reshaping how societies perceive humanity's relationship with nature across countless fronts. Perhaps the most profound lesson lies in how these discoveries have rewritten the narrative of climate education itself. Where students once memorized abstract concepts like sea level rise, they now analyze actual stumps that stood above water just a few generations ago. Theories about ecosystem collapse aren't just models on a screen, they're visible in the pollen records of plants that failed to adapt. This tangible evidence has transformed climate science from a speculative future concern into a visceral, immediate reality with deep historical roots. The classrooms of tomorrow won't just teach about environmental change, they'll use these underwater forests as living laboratories, proving that the past isn't just prologue, it's a roadmap, a warning, and if we're wise, a second chance. Artists across mediums have seized upon these submerged forests as portals to a forgotten world, transforming scientific data into breathtaking visions that stir both intellect and emotion. Painters like Alex Bramman employ paleobotanical studies to recreate prehistoric wetlands with meticulous accuracy. Her canvases alive with towering tree ferns and dragonflies the size of ravens, their iridescent wings catching light that last touched those leaves 50,000 years ago. Meanwhile, digital artists collaborate with marine geologists to build immersive virtual landscapes, allowing viewers to walk through forests now buried under 60 feet of seawater, hearing reconstructed bird calls based on fossilized syrinx bones. These creations do more than entertain, they forge emotional connections to landscapes we'll never physically visit, making abstract climate concepts viscerally real. Literature has embraced these ecosystems as settings for stories that blur the line between research and imagination. Author Eileen Kelsey's novel, The Submerged, follows a marine biologist unraveling secrets in a drowned cypress forest, weaving real sonar mapping techniques into a thriller about love and extinction. Even children's books like Grandfather Tree use the preserved forests to teach about deep time, with illustrations showing generations of woodland creatures living and dying around a single oak before its final submergence. What makes these works remarkable is their fidelity to the science. Authors routinely consult pollen diagrams and sediment cores to ensure their fictional worlds align with climatic evidence. Filmmakers face unique challenges in bringing these vanished ecosystems to life. Documentaries like BBC's Forests Beneath the Waves combine CGI with practical effects, submerging scale models of ancient trees in custom tanks to study how light refracts through their canopies underwater. The recent indie film Mudlark took a radically different approach, shooting entirely in modern mangrove swamps at specific tides to mimic prehistoric flooding events. This dedication to authenticity transforms artistic interpretation into a form of research. When a painter hypothesizes about the coloration of an extinct leaf based on its chloroplast structure, or a filmmaker stages creature interactions matching fossilized trackways, they're contributing to our collective understanding. Perhaps most powerful are the installations that make time tactile. Japanese artist Taro Shinoda suspended hundreds of resin-cast tree rings in a gallery, each disc engraved with climate data from a different millennium. Visitors literally walk through layers of history. In Norway, an outdoor exhibit replants an actual submerged forest. DNA scientists extracted genetic material from preserved pine cones and cultivated saplings that now grow where their ancestors stood before the seas rose. These projects collapse temporal boundaries, letting us touch living fragments of the deep past. What unites all these works is their ability to make us feel the weight of geological time, not as an abstract concept, but as a narrative woven through every leaf and trunk. When a novelist describes characters watching the ocean claim their homeland over decades, or a painter captures the last sunlight filtering through drowning branches, they're translating raw data into human experience. This fusion of art and science doesn't just reconstruct lost worlds. It reminds us that our own landscapes are equally transient, equally precious. The same creative forces that imagine the past might just help us reimagine the future. The remarkably preserved wood from these ancient submerged forests presents a tantalizing paradox. While scientifically priceless, some specimens remain physically usable centuries after their demise. In the Baltic region, artisans have crafted jewelry and musical instruments from black oak salvaged from seafloors, the wood's dense, waterlogged grain producing tones violin makers compare to Stradivarius quality spruce. Yet for every artisan praising its workability, researchers voice concerns. Drilling into a 10,000-year-old trunk for a table leg isn't just destruction, it's erasing climate data locked in those growth rings. The debate mirrors tensions surrounding shipwrecks. When does a relic stop being raw material and become irreplaceable evidence? Tourism offers another economic avenue with equally high stakes. At the submerged forest off Wales coast, low tides reveal a haunting landscape of petrified stumps that draw thousands annually. Local guides lead timed tours across the slippery rocks, educating visitors about preservation protocols like no-touch rules and restricted photography angles. Contrast this with Alabama's underwater forest, accessible only by scuba, where strict permitting limits dives to research teams. Both models show promise, but scale presents problems. What works for a few hundred mindful tourists could collapse under mass visitation, a lesson learned from coral reefs trampled by well-meaning snorkelers. Emerging technologies might solve this balancing act. Virtual reality reconstructions based on LiDAR scans allow public exploration of fragile sites without physical intrusion. Museums increasingly display 3D printed replicas of submerged artifacts, letting visitors handle perfect copies while originals remain undisturbed. Even ecotourism is evolving. Norway's frozen forests snorkeling tours employ marine archaeologists as guides, transforming sightseers into citizen scientists who document erosion patterns. These innovations hint at a middle path where economic value and preservation aren't mutually exclusive. The core challenge lies in shifting perspectives. These forests aren't just resources, they're archives. A single plank sold as novelty lumber represents lost data about rainfall patterns or atmospheric composition. Conversely, responsible access fosters stewardship. Seeing those gnarled roots first and sparks deeper climate awareness than any textbook diagram. As discussions continue, one principle grows clearer. These time capsules survived nature's upheavals through sheer chance. Whether they survive human curiosity depends on the choices we make today. The hunt for Earth's vanished forests is entering its most thrilling chapter yet, with scientists preparing to push the boundaries of underwater exploration like never before. Cutting-edge submersibles capable of descending to previously unreachable depths are being outfitted with laser scanners and DNA sequencers designed to analyze wood samples on the spot. These high-tech missions won't just search randomly, they'll follow ancient river channels mapped by satellite, tracing the submerged pathways that once nourished these lost ecosystems. Teams are particularly excited about the Gulf of Alaska, where glacial retreat has exposed new stretches of seabed that may hold forests buried during the last ice age's rapid melt. What makes these upcoming expeditions revolutionary isn't just their technology, it's their collaborative spirit. Marine archaeologists are teaming up with climate modelers in unprecedented ways, using tree ring data to refine predictions about ocean currents and storm patterns from millennia ago. By cross-referencing these ancient weather records with modern climate simulations, they're uncovering patterns that could explain why some forests vanished overnight while others faded gradually. This synergy between past and present is revealing climate tipping points we never knew existed, critical thresholds that once crossed triggered irreversible changes. Above the waves, space agencies are joining the effort. NASA's upcoming surface water and ocean topography satellite will employ advanced radar to detect subtle variations in sea level that might indicate buried woodlands. Meanwhile, private companies are training artificial intelligence to analyze decades of sonar data, flagging anomalies that human eyes might miss. Early tests have already identified 12 potential sites off Japan's coast, where underwater cliffs could have preserved entire hillsides of cedar trees in sudden landslides. The next decade promises more than just new discoveries. It could rewrite how we study environmental history. Imagine retrieving intact DNA from trees that witnessed the extinction of mammoths, or finding pollen grains that reveal exactly how ecosystems reassembled after abrupt climate shifts. Some researchers even speculate about discovering submerged groves from the Paleocene-Eocene thermal maximum, a period 56 million years ago when global temperatures spiked, a potential parallel to our current trajectory. Yet for all the high-tech tools, the most important breakthroughs may come from low-tech observations. Citizen scientists monitoring coastal erosion after storms have become invaluable allies, often spotting exposed tree stumps before professionals can arrive. In Scotland, local divers recently documented a previously unknown oak forest in just 8 feet of water, its existence hinted at by generations of fishermen's tales about snagging their nets on something woody. What's clear is that these forests still have countless stories left to tell. As exploration expands into the Arctic, where rising temperatures are melting permafrost that once sealed away entire landscapes, who knows what other botanical time capsules await discovery. The oceans have guarded their secrets for millennia, but now, armed with new tools and fresh perspectives, we're finally learning how to listen. One of the most exciting aspects of these underwater forest discoveries is realizing how accessible the science has become. You don't need a PhD or high-tech equipment to contribute meaningfully. Research teams from Florida to Scandinavia actively recruit volunteers for shoreline surveys, where a sharp eye and a smartphone can document exposed roots or unusual sediment layers after storms. These citizen scientists often serve as the first line of discovery, like the retired teacher in Wales who spotted a cluster of oak stumps during an exceptionally low tide, leading to the identification of a 5,000-year-old forest. Many institutions provide free online training modules to help volunteers distinguish between ordinary driftwood and archaeologically significant specimens, turning beachcombing into a treasure hunt with real scientific value. For those who prefer dry land, social media campaigns like #DrownedForests connect global communities to share observations and preservation strategies. A viral TikTok video from a marine biology student in Norway recently demonstrated how to photograph suspicious wood fragments with scale references, simple actions that helped researchers pinpoint 3 new Baltic sites in just 2 months. Meanwhile, crowdfunding initiatives allow small donations to sponsor everything from lab analyses of tree rings to underwater drone rentals for student expeditions. Every shared post or dollar creates ripples, amplifying the reach of underfunded research. Diving enthusiasts play a particularly vital role through programs like Submerged Heritage Watch, which certifies recreational divers in basic archaeological protocols. Participants learn to recognize signs of ancient forests like concentric root patterns in seabed sand without disturbing the sites. In the Bahamas, a dive shop owner trained his clients to map submerged pine stands using waterproof slates, contributing data that filled critical gaps in sea level rise models. The key is balancing curiosity with conservation. Touching or removing wood might seem harmless, but it erases contextual clues about how the forest died. Even classrooms are getting involved. Middle school students in Maine collaborate with oceanographers through Adopt a Forest projects, analyzing sediment samples mailed to their schools and comparing pollen grains to modern plants. High school robotics teams design miniature submersibles to test in university wave tanks, their experiments informing next-gen research tools. These initiatives prove that scientific breakthroughs aren't just made in labs. They can start with a child's question about why tree stumps sometimes appear at the beach. The beauty of this collective effort lies in its diversity. A fisherman's knowledge of tidal patterns might guide researchers to hidden sites. An artist's rendering of a prehistoric forest could inspire new hypotheses about species interactions. Every perspective, whether from a professional or a passerby, adds another piece to the puzzle, because protecting these time capsules isn't just about preserving the past, it's about empowering everyone to help write the future. When a teenager in Alabama can contribute to climate models by photographing a storm-exposed cypress root, science stops being something that happens to us and becomes something we all shape together. Even as these underwater forests rewrite our understanding of ancient climates, they've sparked lively debates among scientists, disagreements that aren't weaknesses in the research, but signs of a field vibrantly alive with curiosity. One of the biggest controversies centers on timing. While radiocarbon dating provides broad estimates for when these forests drowned, some teams argue that local factors, like tectonic shifts or sudden sediment slides, could have skewed the clocks. For example, trees preserved off Norway's coast appear centuries younger than similar specimens in the North Sea, a discrepancy that's led to competing theories. One camp proposes delayed melting of regional ice sheets created localized sea level variations, while others point to underwater landslides that might have buried some forests earlier than others. The truth likely lies somewhere in between, a reminder that Earth systems rarely move in perfect sync. Then there's the puzzle of whether all these sites tell the same story. The Baltic's oak forests and Alabama's cypress stands both drowned as glaciers retreated, but their sediment layers reveal starkly different patterns. In the Baltic, saltwater infiltration was gradual, leaving trees enough time to show stress rings from years of struggling against brackish water. Alabama's forest, by contrast, was swamped so abruptly that some trunks still had green leaves when buried. This disparity has researchers questioning whether we're looking at one global event or a mosaic of regional crises. Could some forest have succumbed to mega storms rather than rising seas? The answer matters profoundly. It shapes how we model modern climate impacts, revealing whether coastlines will fade slowly or vanish overnight. Human activity adds another layer of intrigue. While most submergence events predate civilization, there are tantalizing exceptions. Along India's Konkan coast, submerged mangroves contain pottery shards and charred seeds at their roots, hinting that early agricultural fires may have destabilized soil just as seas were rising. In the Black Sea, a Neolithic fishing village now lies beneath 40 feet of water, its collapse coinciding with both rapid sea level rise and evidence of deforestation. These cases blur the line between natural and anthropogenic change, forcing us to ask, did ancient societies inadvertently accelerate their own disasters? Or were they simply caught in climatic shifts far beyond their control? What unites these debates is their shared spirit of discovery. Every contested tree ring, every disputed sediment layer drives scientists to refine their tools and theories. New laser dating techniques can now pinpoint submergence to within a human lifetime, while isotopic analysis tracks seasonal changes in prehistoric groundwater. The disagreements aren't roadblocks, they're stepping stones, each one leading to sharper questions and deeper insights. After all, if studying the past were as simple as reading a textbook, we wouldn't need those ancient forests in the first place. Their very mysteries are what make them such powerful teachers, reminding us that science isn't about finding final answers, but about learning better ways to ask the right questions. The speed at which those ancient forests vanished beneath the waves should send chills down our modern spines. Sediment cores from drowned landscapes reveal sea levels rising 10 times faster than current projections, entire ecosystems swallowed in centuries, not millennia. What makes this especially jarring is that these catastrophic changes happened without smokestacks, without gas-guzzling cars, without deforestation on an industrial scale. Nature alone flipped the switch, proving our planet's capacity for sudden, ruthless transformation. Now, as human activity cranks the dial on greenhouse gases, we're essentially replicating those ancient climate shifts, but compressing timelines that once spanned generations into mere decades. Those submerged tree rings don't just record history, they're flashing warning lights in a language we're only beginning to fully decipher. Consider the stark parallels. Pollen grains preserved with the forest show how plant communities scrambled to adapt as waters rose. Some species migrated inland, others evolved salt tolerance, but many simply vanished. Today, biologists observe identical struggles in real time. Coastal mangroves retreat uphill until highways or hotels block their path. Freshwater wetlands turn brackish, forcing out native species while invasive competitors surge. The difference this time, ancient forests had room to maneuver across open landscapes. Modern ecosystems are trapped in fragmented patches, their escape routes severed by cities and farmland. It's like watching history replay, but with the emergency exits welded shut. Even more unsettling are the thresholds hidden in the data. Core samples from the North Sea's Doggerland reveal periods of relative stability followed by abrupt collapses, proof that environmental systems can absorb stress until they suddenly don't. Contemporary climate models now identify similar tipping points: glacier melt accelerating past reversibility, ocean currents faltering, permafrost belching stored methane. The submerged forests demonstrate what happens next. Their perfectly preserved leaves and insects capture moments when conditions tipped from survivable to catastrophic, freezing snapshots of ecosystems caught mid-collapse. Scientists liken it to finding a prehistoric fire alarm still screaming its warning across millennia. Yet within these sobering lessons glimmers something unexpected: proof of resilience. Some tree species in those drowned forests left behind genetic descendants that thrive today, their DNA bearing scars of ancient adaptations. Modern conservationists now use these blueprints to engineer climate-resistant crops and restore wetlands. The past isn't just a horror story, it's a survival guide written in cellulose and sap. Those forests whisper that extinction isn't the only possible ending. Transformation is equally woven into Earth's story. The question isn't whether change will come, but whether we'll heed the patterns etched in those waterlogged timbers. After all, the trees didn't choose their fate. We still can. Exploring these ancient underwater forests doesn't come easy. It's a race against physics, funding, and the sheer unpredictability of the deep. Even with cutting-edge technology, reaching these submerged time capsules means battling crushing water pressure, limited visibility, and equipment that can fail in the blink of an eye. A single research dive to document a forest 60 feet down might cost tens of thousands of dollars, requiring specialized ships, trained crews, and submersibles built to withstand the ocean's relentless squeeze. And that's just to reach the site. Bringing samples to the surface is another high-stakes gamble. Wood preserved for millennia in oxygen-starved mud can begin deteriorating within hours of exposure to air, turning priceless climate records into sludge before scientists can stabilize them. Preservation is its own nightmare. Laboratories studying these artifacts need humidity-controlled chambers that mimic the seabed's cold, dark environment. Facilities so precise they're often compared to operating rooms. A single fluctuation in temperature or humidity can erase delicate cellular structures or distort tree rings that hold centuries of climate data. Some institutions have resorted to storing recovered wood in custom tanks of chilled seawater, buying time to analyze them before time catches up. Even then, the clock is ticking. The very conditions that saved these forests, lack of oxygen, steady pressure, are nearly impossible to replicate on land, leaving researchers scrambling to extract data before the artifacts crumble. Then there's the puzzle of ancient DNA. While headlines tout miraculous recoveries of genetic material from submerged specimens, the reality is far messier. Saltwater, pressure, and time degrade DNA into fragments so tiny that sequencing them is like reconstructing a shredded encyclopedia from half its pages. New techniques like hybridization capture can fish out specific genetic sequences, but contamination is a constant threat. A single touch from a modern human or a bacterium hitching a ride on equipment can skew results irreversibly. Scientists now work in clean rooms resembling semiconductor labs, suited head to toe in sterile gear to avoid introducing even a speck of modern DNA. Yet for every obstacle, innovation rises to meet it. The same pressures that make deep-sea exploration so daunting have birthed astonishing workarounds. Underwater drones equipped with robotic arms can now collect samples without surfacing, sealing them in pressurized pods that maintain seabed conditions all the way to the lab. Portable DNA sequencers no bigger than a smartphone let researchers analyze genetic material on site, reducing the risk of degradation during transport. Even artificial intelligence plays a role. Machine learning algorithms can now fill in gaps in fragmented DNA sequences by comparing them to databases of modern relatives, effectively resurrecting genetic blueprints thought lost forever. What's remarkable isn't just the technology, but the collaboration driving it. Oceanographers team up with aerospace engineers to adapt satellite mapping for the seafloor. Biochemists borrow CRISPR techniques from medical labs to repair ancient DNA. Citizen scientists scour satellite images for telltale shadows that might reveal new sites. The challenges haven't deterred progress. They've fueled a golden age of interdisciplinary problem solving. And perhaps that's the most enduring lesson these forests teach us. The same ingenuity that's unraveling their secrets could one day help our ecosystems adapt to a changing world. Every tool perfected to study the past becomes a potential lifeline for the future, whether it's a drone that monitors modern mangrove health or a database of ancient drought patterns that informs today's water policies. The difficulties aren't just hurdles, they're invitations to think bigger, dig deeper, and remember that the greatest discoveries often lie just beyond the edge of what we think is possible. These submerged forests aren't just time capsules for climate scientists, they're treasure troves for researchers across disciplines, each peeling back layers of meaning from the same ancient wood. Marine archaeologists, for instance, study not just the trees themselves, but the artifacts nestled among their roots. A stone tool wedged in a submerged cypress stump off Florida's coast tells a story of human adaptation, proving that early coastal communities harvested these wetlands for resources long before the seas rose. Similarly, the fishing weirs found entangled in Denmark's drowned oak forests reveal sophisticated knowledge of tidal patterns, knowledge that vanished when the landscapes did. These finds rewrite human history, showing how cultures thrived in environments we'd consider marginal today, only to disperse or reinvent themselves when those worlds disappeared beneath the waves. Biologists, meanwhile, are reconstructing evolutionary puzzles from DNA fragments preserved in the silt. A beetle's wing casing found in Baltic peat matches no known species, hinting at lost branches on the tree of life. By comparing the genetics of submerged forest plants to their modern descendants, researchers track how species adapted or failed to adapt to rising salinity and temperature swings. Some discoveries border on surreal, like the intact pollen grains from an extinct flower that now help botanists understand why certain plant families survived climate upheaval while others vanished entirely. These aren't just academic exercises, they're roadmaps for conservation, showing which genetic traits helped organisms endure past extremes, lessons that could prove vital as modern ecosystems face similar stress. For climate modelers, these forests offer something even more precious, real-world data to test their predictions against. Supercomputers can simulate future sea level rise, but how accurate are those projections? By comparing the models to actual events preserved in tree rings and sediment layers, scientists spot flaws in their assumptions. The submerged forests reveal surprises, like evidence that some coastlines sank faster during past warm periods than current models anticipate. Others show how ocean currents shifted when ice sheets melted, altering rainfall patterns thousands of miles inland, a ripple effect many climate simulations underestimate. This historical reality check is transforming how we forecast everything from hurricane frequency to agricultural viability, grounding speculative models in Earth's own hard-won experience. Geologists contribute another layer to the story, reading the seabed like a historical novel. The sand deposits surrounding Alabama's drowned cypress trees, for example, tell of catastrophic storms that pummeled the coast as the Ice Age ended, events that left distinct sediment signatures now recognized in modern hurricane deposits. In New Zealand, the way kauri trunks lie jumbled across ancient valleys points to massive landslides triggered by earthquakes, offering clues about tectonic activity during periods of rapid climate change. These physical records don't just describe the past, they help predict where and how future geological hazards might unfold as our planet continues warming. What emerges from this interdisciplinary mosaic is a profound truth. No single field holds the key to understanding these lost worlds. The anthropologist mapping prehistoric settlement patterns needs the climatologist's sea level curves. The biologist tracing genetic adaptations relies on the geologist's timeline of land subsidence. Together, they form a collective lens, each perspective correcting and enriching the others. It's a reminder that the biggest questions, how environments change, how life responds, how civilizations endure, can't be answered in isolation. The submerged forests teach us that the boundaries between disciplines are human inventions, while nature itself is gloriously, messily interconnected. And perhaps that's the most enduring legacy of these underwater time capsules. They don't just belong to marine biologists or archaeologists. They're living laboratories for anyone curious about Earth's past and our planet's future. Whether it's a medical researcher studying ancient plant compounds for new antibiotics, or an urban planner drawing lessons from prehistoric coastal communities, these forests keep giving. Their rings and roots and pollen grains whisper across millennia, offering not just warnings but wisdom if we're willing to listen with all the tools at our disposal. These ancient underwater forests are more than scientific curiosities, they're living classrooms. They're lessons etched in bark and sediment. Every tree stump, every preserved leaf, every insect trapped in time whispers the same truth. Earth's story is one of constant transformation. These drowned landscapes witnessed climates flip from ice ages to tropical warmth, saw shorelines redrawn by rising seas, and watched entire ecosystems vanish or reinvent themselves. Yet within their rings lies another revelation, proof that life persists, even in the face of cataclysmic change. The same trees that succumbed to salt water left descendants adapted to thrive in new conditions. The ferns that vanished from one region flourished elsewhere. Extinction is real, but so is reinvention, and that duality holds the key to our own future. What makes these submerged forests so urgent isn't just their warnings about rising temperatures or shifting coastlines. It's the way they expose the fragile threads connecting all life. A beetle preserved in Baltic amber isn't just an insect, it's a pollinator whose disappearance might have doomed certain plants. A buried river channel isn't just a geological feature, it's the freshwater lifeline that sustained forests, animals, and human communities. These ecosystems remind us that environmental collapse is never isolated. It ripples outward, touching everything. Yet they also demonstrate nature's breathtaking creativity in responding to upheaval. Where one door closes, another opens, sometimes literally, as land bridges drowned by rising seas became fertile fishing grounds for displaced communities. The most humbling lesson isn't about the past, though. It's about perspective. Standing on a modern shoreline, it's easy to assume our landscapes are permanent. But these forests shatter that illusion. The very ground beneath us has been rearranged before and will be again. That's not a cause for despair, but for clarity. Understanding how change unfolded millennia ago helps us navigate it today, whether it's coastal towns planning retreat strategies or conservationists identifying which species might adapt fastest. The past doesn't offer blueprints, but it does provide compasses pointing toward resilience in the face of uncertainty. So what do we do with this knowledge? First, we listen. These forests spent millennia waiting to be heard. Their data can guide smarter policies and bolder conservation. Second, we protect their modern counterparts, the mangroves, peatlands, and old-growth forests currently standing between us and climate chaos. Finally, we recognize that we're not just observers of this story, we're its authors now. The same forces that reshaped those ancient worlds are at work today, but this time human hands are on the levers. That's a staggering responsibility, but also an extraordinary opportunity. If these submerged sentinels teach us anything, it's that endings are also beginnings. Every drowned forest became a reef, every vanished wetland a nursery for new life. The question isn't whether change will come, it's how we'll meet it. Will we fight blindly against forces we can't control, or will we adapt with the wisdom of those who came before? The answers might just lie beneath the next wave, waiting to be rediscovered. For now, these ancient trees keep their vigil, reminding us that time is long and life, in some form against all odds, finds a way. Your thoughts shape these explorations as much as the science does. What other hidden histories should we uncover? Share your ideas below, and if you've enjoyed this dive into Earth's forgotten chapters, join us for the next adventure. The past has never been more alive or more relevant. Until then, keep looking deeper. The most extraordinary stories are often the ones we